Well, it's 8 o'clock and time for the Monday morning lecture. So recall the squeeze theorem for limits. If f of x is less than or equal to g of x, which is less than or equal to h of x, when x is near the number a, except possibly at a itself, and if the limit of f of x as x approaches a is equal to the limit of h of x as x approaches a, if that limit is equal to L, then the limit of g of x, which is between f of x and h of x, also must have a limit equal to L as x approaches a. So a simple illustration, if we have the xy plane, and if we have some function h of x that looks something like that, and another function f of x, which is below h of x, so this one's y equals f of x. And then if another function is between f of x and g of x, so the graph of the red function is y equals g of x, then you can see that in this illustration that the limit of g of x as x approaches a has to be equal to the limit of h of x as x approaches a, and also the limit of f of x as x approaches a. Well, with that in mind, let's evaluate the following limit. The limit of 1 plus x to the 1 over x as x approaches 0. Notice if you've been exposed to limits for any amount of time, you know that there are some limits that can be evaluated by direct substitution. But in this case, if we replace x with 0, then the exponent is undefined because 1 divided by 0 is undefined. So we'll do a couple of algebraic maneuvers. For values of x greater than -1, the 1 plus x to the 1 over x can be expressed as e to the natural log of 1 plus x to the 1 over x. So this is just using a property of logarithms and exponents. I'll just make a note of it up here. If a number b is greater than 0, then b can be written as e to the natural log of b. So we just applied that to the expression 1 plus x for values of x greater than -1. We need x to be greater than -1 because the argument of the natural log has to be positive. Okay, then using properties of exponents, here we have e raised to the exponent, the natural log of 1 plus x, and this entire expression is raised to the exponent 1 over x. One of the properties of exponents says that we can multiply this exponent by that exponent, and so we get e to the natural log of 1 plus x over x, because 1 over x times the natural log of 1 plus x is just the natural log of 1 plus x over x. And since we're computing the limit of this, our limit can be thought of as e to the limit as x approaches 0 of the natural log of 1 plus x over x. Okay, so once again, we have the problem of, well, we can't evaluate this limit by direct substitution because that would give us a denominator of 0, which means the expression is undefined. So to get around that, I'm going to do the following. For values of x that are between negative 1/2 and positive 1/2, I'm restricting x to this interval, which is okay because eventually we want to find the limit as x goes to 0. So this interval contains 0. And for x between negative 1/2 and 1/2, it turns out that x minus x to the second is less than or equal to the natural log of 1 plus x, which is less than or equal to x. I won't do it here, but you can pretty easily graph the three functions on the interval from negative 1/2 to 1/2, and you can show that the natural log of 1 plus x is between x minus x to the second and x. Okay, we want to find the limit of the natural log of 1 plus x over x. So now we're going to divide everything on both sides by x, but we have to do this in a couple of segments. First, for x that is positive and between 0 and 1/2, but not including 0, if we divide each of the three parts of this compound inequality by a positive number, then we get x minus x to the second over x is less than or equal to the natural log of 1 plus x over x, which is less than or equal to x over x. And then if we simplify those expressions, x minus x squared over x, that simplifies to 1 minus x, which is less than or equal to the natural log of 1 plus x over x. Whoops, over here I'm dividing by x. This should be x over x instead of x over 1. But x over x is equal to 1. Okay, now we can use the squeeze theorem at this point. That was discussed above. So we take the limit as x approaches 0 of 1 minus x. We can evaluate this by direct substitution. And the limit of a constant is just the constant. So this limit is equal to 1. And so by the squeeze theorem, the limit of the function that is between 1 minus x and 1 must also be equal to 1. All right, but what about the negative x values? So this time for values of x that are between negative 1/2 and 0, not equal to 0. Well, when we divide each of the three parts of this inequality by a negative, we have to, since we're dividing by a negative, we have to switch the direction of the inequalities. So this will become x minus x to the second over x greater than or equal to the natural log of 1 plus x over x, which is greater than or equal to x over x. And then if we simplify again, x minus x squared over x, that simplifies to 1 minus x is greater than or equal to the natural log of 1 plus x over x, which is greater than or equal to 1. And then once again, using the squeeze theorem, we take the limit of the left-hand side and the right-hand side as x approaches 0, and that implies that the limit of the middle function as x approaches 0 is equal to 1. Okay, so if you recall what we were trying to do, we were trying to find the limit of 1 plus x to the 1 over x as x approaches 0. So we found that the limit as x approaches 0 of 1 plus x to the 1 over x, this is equal to e to the limit of the natural log of 1 plus x over x, or e to the first power, or e. So recall the number e. E is approximately 2.71828, and so on. Okay, the next page. Well, we'll consider the same problem, but a different method. But we do know that the limit of 1 plus x to the 1 over x as x approaches 0 is equal to the number e. But this time we'll show that the limit of the natural log of 1 plus x over x as x approaches 0 equals 1 by using an infinite series. So let's start by saying if y is equal to the natural log of 1 plus x, then the derivative of y with respect to x is equal to 1 over 1 plus x. And we can think of 1 over 1 plus x as the sum of a geometric series, provided that the absolute value of x is less than 1. Okay, so I'll just make a note. Geometric series 1 over 1 plus x, if we think of this 1 over 1 plus x as 1 over 1 minus negative x, according to the geometric series sum formula, 1 over 1 minus negative x is what the series converges to. So if we write 1 plus negative x to the first plus negative x to the second plus negative x to the third, and so on. And this is for values of x that have an absolute value less than 1. So more to the point, we can write that 1 over 1 plus x is equal to 1 minus x plus x squared minus x to the third plus x to the fourth, and so on. In sigma notation, we can write this starting at n equals 1 and going to infinity. We can write this as negative 1 to the n minus 1 times x to the n. Sorry, x to the n minus 1. Okay, but remember what 1 over 1 minus x is. That's the derivative of the natural log of 1 plus x. And so by computing antiderivatives, the natural log of 1 plus x is equal to the indefinite integral of 1 over 1 plus x dx. And then what we do is we just find antiderivatives of the infinite series for 1 over 1 plus x. And then we include the constant of integration. So the constant of integration c, and then an antiderivative of 1 with respect to x is x. An antiderivative of minus x with respect to x is minus x squared over 2. And so on. The next one is plus x to the third over 3, then minus x to the fourth over 4, and so on. To determine the value of the constant of integration, well, we can pick x to be 0. When x is 0, the natural log of 1 plus 0 is the natural log of 1. And on the right-hand side, replacing every x with 0, the only thing left is c. But we know that the natural log of 1 is equal to 0, so that means that c is equal to 0. Okay, so the natural log of 1 plus x is just x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4, and so on. And then, remember what we're trying to do? We're trying to find the limit of the natural log of 1 plus x over x as x goes to 0. So in the next step, we'll just divide both sides of this by x. We get the natural log of 1 plus x over x. Divide each of the terms on the right-hand side by x. X divided by x is 1. And then minus x over 2. And then plus x to the second over 3. And then minus x to the third over 4, and so on. And when we take the limit of this as x approaches 0, the limit of the natural log of 1 plus x over x as x approaches 0. And then when we take the limit of the right-hand side as x approaches 0, there's only one term that is not affected by x. The only term that survives is 1. All of the other terms go to 0. And so this is a second way to show that the limit of the natural log of 1 plus x over x as x approaches 0 equals 1. There's a third way that we won't discuss. I'll just mention it. L'Hopital's rule can also be applied but we'll save that for another day. So that's all for today.